you're welcome back again. So we are going to look at another algorithm under association called FP growth. So FP growth is a frequent item set mining algorithm that discovers patterns, e.g., items often bought together without candidate generation, making it faster than a priori, which we did last time. So it uses a compact FP tree rather, which is called frequent pattern tree, to represent transactions and recursively mines frequent item sets. Now there are key concepts here, which one of them is called the FP tree. Okay, in structure wise, a comprehensive tree where nodes represent items with frequency counts, path represent transactions, e.g., milk to bread to egg. So that is the path. So we also have header table, which stores item frequencies and link it to trees node for fast access. Conditional pattern base: for each item, we extract all paths from the FP tree that end with that item. For example, eggs, path might be milk bread, then bread one. So we have two here, we have one here. All right. So we also have recursive mining. Mine the FP tree by starting from the least frequent item in the header table, building its conditional FP tree, that's a projected database, and repeating until no more frequent items can be found. Okay, we have support count, minimum frequency threshold for an item set to be considered frequent. Be considered frequent as this way, when the higher the count, the higher the frequency. Okay, so the minimum support we have is 0.3, which is 30% transaction. So how does it work now, step by step? The first thing we build what they call FP tree, which scans transaction to count item frequency. We create a tree where path represents frequent item, e.g., bread to milk to butter. We also create we mine frequent item set by starting from the bottom of the tree, which is least frequent items. For each tree, for each item, we construct its conditional pattern based on recursively mine. Then we also have a rule generation, which derive rule from frequent item set using metrics like confidence or lift. So let's see how we implement this quickly by using the groceries market basket data set that we used last time. So we import our data set here now on libraries. So we have our data set here, so you can just see a sample here. This is a one hot encoder. So we already have here, so the true equals to item purchased in that transaction. So that is called true. So you can see butter, bread, butter, cheese, egg, milk. So true here under butter. So we can only apply our FP growth here, okay, which mines frequent item set without candidate generation, unlike a priori. So here we have our item set support. We have item set here. And looking at this now, you understand that bread appears in 85% of transaction, or approximately 86% anyway. So you can just say, okay, 86% of bread appear here. And we also have bread and milk co-occurs in 58% here. So the co-occurrence of bread and milk 57% here. Can you see here bread and milk here 7%? So of transaction, we can generate our association rule now by extracting rules from frequent item set using confidence or lift metrics. So here we supply our confidence metric here, right? So this is our metric. Don't forget is confidence. Our minimum threshold is 0.6, which is 60%. Okay, so running this, we have our antecedent, we have our consequence, we have our support, our confidence, and lift. All right. So looking at this now, you can understand that butter to milk now, you can see butter, we trace butter here, that is butter to milk here, see that to milk here. All right, okay, that's 75%. That's confidence now. Confidence 75%. Okay, of butter, also buy milk. Okay, those 75% of people who buys butter rather buy milk. So the lift is more than 1, which is positive correlation. So we have 1.05 of the lift. Then we also have a double here. We have a milk and butter here. Okay, milk and butter are here. Okay, with bread. This is a 100%. Can you see confidence 100%? Okay, and the lift is 1.12 approximately. It's more than 1. So all who bought milk and butter also bought bread. All, not 1, not 2. Or don't forget here, only 75% of butter buyers that also buy milk. Okay, now but here all, that's why it's 100% confidence. Okay, all right. So because the higher the lift, the stronger the association. All right. So you can move on gradually. Now you can say, okay, we have some key parameters that can be changed here. So we have minimum support, which is lower value, return more item set, but lower. The recommended value is between 0.01 to 0.1. Minimum confidence rules with lower confidence are filtered. So filter out. Recommended value is 0.5 to 0.7. We use 0.6, which is better in the range. We have metric can use a lift or confidence or support for filtering. Recommended value is lift greater than 1, which is strong. Okay, so we can visualize these rules by plotting our bar plot here. You can see top 5 association rules by lift here. So we have this 1, 2, 3, 4, 5. Okay, so you can see. So higher bars is equal to stronger association. Right? We have milk, butter to bread, which has a 1.4 lift. Okay, milk butter. If you check here, milk butter to bread here, you can see. So that's 1.4 here. This 1.4, not up to 4, this 1.2, not up to 1.2 actually. But here we have bread, butter, milk. All right. So this is your milk, butter, bread. So also we can also plot our what they call it now, its map here, right? Its map. When you cut out this map, we have support values of frequent item set. So the highest here is 0.86, which is more darker. Okay, the darker it is, the higher it is. So the higher it is, so you can see this followed by 0.71, which is a milk. The first one is bread. Okay, the bread here, and followed by milk. Okay, see here, darker cells means higher support, e.g. bread has the highest support. Okay, so key parameter also can change here, minimum support, lower value, return more, which I've explained before. Use columns, use item names instead of column name indices in the result, which is true. Maximum length of the my item set, which should reduce computation 2 to 5. For larger data set, we reduce minimum support frequency item set, which equals to FP growth, and we can pass this in. All right. So network graph association rule show relationship between antecedent and consequence with a network diagram. You see diagram here, you can see diagram here, network here, association rule, network edge detection and lift. You can see milk, butter, right, bread. You can see here, right, you can see diagram. So nose item set, e.g. butter, edges, rules, thickness equals to lift strength. All right. Key inside thicker edges indicate stronger association, e.g. butter to bread. All right. So the visualization for how we visualize now, you can see that the heat map quickly identify high support items, while network graph revealed complex relationship between item sets. So we have a bar plot ranks rules by business impact. Okay, using lift. Okay, for large data set, we must understand that we must sample the top 20 rules to avoid clutter in the network graph. Of course, you'll not be able to see everything, so you need to sample 20 rules. All right, advantages of a priori, of epic growth now, rather not a priori. But advantage of FP growth over a priori, what I meant, advantages over a priori. So he has advantage over a priori. Number one is speed. FP growth is faster, no candidate generation required anyway. So a priori is lower, exponential candidate is required. So for memory, FP growth compacts FP tree structure. A priori has a high memory for candidate set. Right? Scalability, FP growth handles large data sets better. A priori struggles beyond 10K items. So these are just basically what we need to learn about our FP growth classification association based algorithm, which you just saw now. So we can continue from there the next time. So I'm going to stop here for now. So thank you so much for listening. I will see you on the next class as we look to something totally different. Thank you.